And when we're having to add or subtract things, or when we're having to multiply or divide things, that changes the way we look at the significant figures that go into our answer. Okay? So there's different rules that apply for when you're adding and subtracting numbers or when you're multiplying and dividing numbers. Okay? So when you're adding and subtracting numbers, we're going to do the math first. You always just do the math, and then you're going to look at rounding your answer to the correct number, significant figures. Okay? So do the math first, then we're going to round our answer to correspond to the least precise value involved, and that means we're looking at the number of decimal places. Okay? So when we add and subtract, we're looking at decimal places, okay, or decimal points. Okay, so the least precise would mean we're rounding to the smallest number of decimal points. Okay, so when you add and subtract, you're going to round to least number of decimal points. Okay, so there's a little abbreviated version of that top section. When we add and subtract, we want to round to the least number of decimal points that we started with, one of our numbers that we add and subtracted. Okay, so if we take a look at this problem, I did the math for you. So now we want to look at the number of decimal points. Our first value has how many decimal points? Decimal points? We have 3 decimal points. Okay? Whereas our second number only has 1 decimal point. Our final answer, we need to be rounding to 1 decimal point. So how do I round 26.520 to 1 decimal point?
26.5.
26.5. That's it. Okay? So the reason that happens is because if one of my measurement tools is much less precise, that means that my answer can't be any more precise than that. Okay? If one of my measurement tools only allows me to measure to 1 decimal place, I can't have an answer that's got 3 decimal places because that contradicts each other. Okay? So just think about it in terms of that. All right, questions there? Okay. 1 decimal place, we round to 26.5. Now when we multiply and divide, we do the math, then round your answer to the same number of significant figures as your least precise measurement. Okay, so when you multiply and divide, you're looking at significant figures now, not decimal places. Okay? So multiply or divide, round your answer to the same number of sig figs as your least precise measurement. Okay, so round to fewest number of sig figs. And that's when you're multiplying or you're dividing. You're going to round to your fewest number of sig figs. How many significant figures do each of these factors have? How many does my first factor have? 3 significant figures right here. Right? 1, 2, 3. This 0 is to the right of the decimal point after digits, so it's significant. Okay, did we all say 3 there?
Yep.
I thought I heard it 2. Okay. 3 significant figures. How many significant figures does 12 have? 2. Is 12 ambiguous?
I don't know.
No, it's not ambiguous. Ambiguous means we aren't sure how many significant figures there are.
Oh, yeah.
Okay, the reason that 12 is not ambiguous is because it doesn't have those trailing zeros. Right? If it was 120, then it might be an ambiguous number. Okay, 12 is not ambiguous. It has 2 significant figures. So our answer can only have how many significant figures? 2. So how do we round 28.8 to 2 significant figures? Yeah, good. We're going to round up to 29. Very good. There's another way we could express this with 2 significant figures. How is that?
22.8 times 10 to the 2.1.
2.9 times 10 to the first.
Oh, I think.
Okay, 2.9. If we were going to use 2.8 times 10 to the first, it would give us a value of 28, which is not as close to our answer as 29 is. So we'd use that 29. You can express that either way. Okay, I'll take it either way in scientific notation or out, as long as this number of significant figures are correct. Good, good. Let's try some here. Okay, go ahead and do these on your own, and then we'll check. I want the answer in the correct number of significant figures. Huh? 319.7. And our answer should have how many significant figures? 2. Okay, our answer should have how many significant figures? Only 2. So, Caitlin, what do you think the best way is to express this with the correct number of significant figures? 320. Okay, how many significant figures does this value have?
2.
Some of you said 3, some of you said 2. That's the point. It's ambiguous. This is ambiguous. It's got a trailing 0, no decimal point, and no scientific notation. Yeah.
3.2 times 10 to the second.
Perfect. We're going to fix it by putting it in scientific notation. 3.2 times 10 to the second. Okay? So the reason 320 doesn't quite work is because it's that ambiguous value, and we want it to only have 2 for sure. So by putting it in scientific notation, it gives us the correct number of sig figs. Does that make sense? All right, very good. Okay. Why couldn't we just do 3.1 times 10 to the second?
You have to round.
Yeah, we have to round. If we did 3.1 times 10 to the second, that would lead us to believe it's somewhere more around 310, when really our answer is more around 320. Okay? Very good. Let's look at the next one here. This is an addition problem, so go ahead and do this one on your own, and then we'll check. Raw answer before you rounded anything? 26.281. Do we agree? Okay. Ivanka, can you tell me? Oh, you missed maybe this part. Do you know how many decimal places we want to round to? The reason that we round to 1 decimal place is that's the fewest number that we were given. So this has 3 decimal places. This only has 1. This has 2, and that has 1. Okay, so we want to round our answer to 1 decimal place, which means our final answer should be 26.3. Good. 26.3. Good. Any questions there with math on sig figs? Is that a review, hopefully? Good. Very good. Okay. If you are a master at scientific notation, you don't have to worry about writing any of this down, just at least listen along, okay? Because some people get tripped up with scientific notation, so I want to make sure that everyone is on the same page, okay? Scientific notation is expressed like this: m times 10 to the n, okay, where n is our exponent. M has to be between 1 and 10, so it can be no greater than 10, but it can't be less than 1. It has to be greater than 1, okay? So m has to be between 1 and 10. The reason that we bother with scientific notation is that it gives us really greater freedom to express really large numbers and really small numbers, and we can be specific with how many significant figures that we want to express scientific notation in. Okay, so scientific notation gives us a lot of freedom in terms of expressing numbers. Really large numbers, really small numbers, or to a specific amount of significant figures. Okay, so we have a lot of more freedom there. So let's say I want to express this value, 124,215. I want to express this value in scientific notation with 3 significant figures. Okay, so let's go ahead and do that on your paper first, and I'll come around and take a look. Okay, so try that in your notes, and I'll come around and look at that. So the way we're getting our final answer, which was supposed to be 1.24 times 10 to the 5th, okay? This is our final answer, and this is how we got there, okay? First of all, I want to express a really large number, right? My number that I want to express right here is larger than 10, yes? Okay, that means my exponent is always going to be positive in that case, okay? Because my number that I want to express is greater than 10, my exponent is going to be positive, okay? The number that goes right here, my m value, always has to be between 1 and 10. So all I'm doing here is taking my number that I want to express, 124,215, and I need to put it between 1 and 10. So I'm going to stick my decimal place right there. Okay, that gets my number between 1 and 10. Yeah?
Yep.
From there, I'm going to move my decimal place until I reach the number I'm trying to show. So I'm moving it 1, 2, 3, 4, 5 places to get to my final answer, which leaves me 1.24 times 10 to the 5th. Okay? If I wanted more significant figures, I could say 1.24215 times 10 to the 5th. I could take as many of those numbers as I want, depending on the number of sig figs that I want. Does that kind of make sense? A little bit better? All right, let's do a couple more. Let's see here. What if I want to express this value in scientific notation? 0.000421. Okay? I want this value to be expressed with 2 significant figures. Okay, so I want you to try to express this value with 2 sig figs. Good. Okay. Allie, can you tell me what you got here?
I don't think I did it right.
Try me.
4.
Okay, so we got 4.2 times 10 to the negative 5th. Why did we drop that 1?
Because you only want 2 significant digits.
Yeah, just because I specifically asked you for 2 sig figs, that's the only reason. Okay, if I don't ask you for a specific number of significant figures, you could keep as many there as you want. Okay, so it's negative 5th because I'm basically, here's my number I want to express, 0.0000421. I'm going to put my number between 1 and 10 by sticking my decimal place there. Then I move 1, 2, 3, 4, 5 places. The number that I wanted to express is less than 1. So I'm going to have a negative exponent here, negative 5. Okay, I know some people try to memorize if I'm moving to the left or if I'm moving to the right. That's when my exponent is going to be negative and positive. I think that gets to be confusing. So just think about the number you want to express. Is it greater than 10 or less than 1? That's going to tell you if your exponent is going to be positive or negative. Does that make sense?
Yep.
Okay, do we need to do a couple more?
Yeah.
Okay, let's try a couple more. Let's try this one. I'll put the commas in for you. Okay, those are commas.
How many?
Let's put this into 3 sig figs. Okay, so let's try these next two on your own. We're going to put both those into scientific notation. Just go ahead and give the final answer. What you got?
Oh, yeah,
Should be a 9.
Yeah.
Yeah, if there's a round thing, All right, very good. Let's take one out of scientific notation now. Okay, so if I give you 4.31 times 10 to the third and 4.25 times 10 to the negative second, I want you to expand both of those numbers. Write the full number out for me. So our answers here should have been 4,310 and 0.0425. Okay, the positive exponent tells us that our answer, our expanded version, should be greater than 10, right? Which it is. 4,000 is greater than 10. Here our negative exponent tells us that our answer should be less than 1. Okay, so move that decimal place to the correct version. All right. Okay, we're going to quickly cover a little bit of the scientific method, models, laws, and theories. This is basic stuff you've heard probably, 4 or 5 times, but we're going to just cover them really quick, okay? I'm not going to go through the scientific method. You guys have heard the scientific method since you were in 2nd grade, okay? We're not going to talk through the scientific method. We're just going to kind of hit on models, theories, and laws and what they mean scientifically. Yeah. The chart on the side doesn't have to be written down. Just those bullets about models, theories, and laws. Okay? So I'll let you go ahead and get it written down, and then I'll explain just a couple things I want you to focus on with each of those 3. Okay? So I'll give you a second to get them written down. Okay, so I'm just going to touch on a few points on each of these. Models can come in lots of different forms. Okay, lots and lots of different ways. And the way that we're going to focus models in this class is usually with a diagram. Okay, so we're going to talk about lots of different equations in physics. We're going to talk about lots of different laws of physics. And the way that we're going to use models is in terms of a diagram. Okay, when we have a physics word problem that's given to us, we want to first and foremost draw that situation out. Okay, so we might have an example problem that says, I throw a ball up into the air, and I'm going to determine how high that ball is going to go, right? I want to determine the distance that it's traveled into the air. So the only thing that I might be doing here Here's my ball. I'm going to throw it up into the air, and that's its stopping point, okay? This, as simplistic as it is a diagram, okay, is a model. It's showing me what my situation is looking like. Whereas if I was going to say I threw it and it traveled both horizontally and vertically, okay, it traveled in that kind of parabola path, that parabolic path, then that might be a different version of that same problem that I'm having to draw out. So the models are going to tell us what's happening in our problem. Where's our object going? What's it look like? What's it doing? Okay, so the models that we're going to use in this class mostly come in forms of very simplistic diagrams. And drawing those diagrams based on the problem is going to become really important. Okay. Laws are what basically means we've reached a final kind of point on a certain idea. Okay, so a law has been tested and tested and tested and tested and never disproved. Okay, so things like Newton's laws. How many laws does Newton have?
3.
3 laws. Okay, we're going to cover all 3 of those. Newton has 3, and they've never been disproven. Right, so they've been tested over and over and over again and never been disproven. It doesn't take maybe 1,000 experiments for a law to become a law. Right, it doesn't have to meet a certain requirement. It's not like a checklist that something has to meet before it becomes a law. It becomes a law just after basically a certain amount of point the scientific community has accepted that it hasn't been disproven, and it most likely won't be disproven. Okay? It becomes this law. Theories kind of give us a little bit of an explanation. So a law is pretty cut and dry in scientific terms. A theory gives us maybe an explanation of what that law is doing and why it's doing it in its surroundings. So just a little bit more on that. Okay. We talked about all of our significant figures. We talked about all the math that goes into it. Now let's look at what we do when we want to measure something, okay? And talk about our different measurement systems. Okay, so the reason that we take measurements is to make a quantity of a certain observation. So I observe something. I want to see how long it is, or how tall it is, or how fast it's going, or how much does it weigh. Okay, those are all observations that I want to quantify by a measurement. I can take a really informal measurement by saying that object is longer than the other, it's moving faster than the other, it's whatever, it's, I don't know. You can basically make a comparison measurement, you can make an estimate measurement, or you can make really accurate and precise measurements. Does anyone know the difference between accuracy and precision? Have we heard those 2 terms before at least?
Yeah.
Accuracy and precision, but we can't remember which is which.
What accurate?
Okay, precision is how close together our measurements are. How close together our measurements are. I'm seeing how little variance there are within the numbers. Okay, so I want really precise measurements, which means we want all of our measurements to look similar and be within a really, really tight range. Okay, whereas if I want to look at accuracy, that tells me how close to the actual value I am. Okay? How well your results agree with the accepted or the actual value. So I want you to think accurate is close to actual. Okay? Accurate is close to actual. Okay, accurate is close to actual. So I'm going to kind of put up a little visual for us here. Oh. I used to be able to draw this okay. No, I can't anymore. That's pretty good. All right. So let's take a look at my target here. If I get 10 shots at a target, and here's my 10 shots, are my measurements very precise? No. Do I have maybe one accurate measurement? Maybe two? Okay. This measurement right here is pretty close to the bullseye. Not all that close. Okay, so my average here, do you think my average measurement here is very accurate? No. Do I look like I have very precise measurements either? No. Okay. Whereas if in the next round, let's say I take another 10 shots. Okay? So this is my second try. Very precise, but not very accurate. Okay? Very precise, not very accurate. So my first round, I might have had one accurate shot, but my average was not accurate. So I really can't consider that accurate either. My second round, really precise, but not accurate. Okay? So ideally, when I take 10 really great shots, I want them to be here. Okay? My average then becomes pretty accurate, right? And they're all precise, which means they're really close together. So ideally, we want measurements to be both accurate and precise. Okay, does that target make sense a little bit? Okay, so we need them to be both. I want you to just brainstorm ways that measurements could be one but not the other. How is it that a measurement could be one but not the other? How could it be accurate but not precise? And how could it be precise but not accurate? Okay, we just kind of looked at an example, didn't we? Yeah, you can raise your hand and explain it if you have it. Here. So this is comparing precision and accuracy. Read through, then give me an A, B, C, or D answer. Just raise your hand or something when you're done.
It's actually 980, and his estimate is pretty close to 980, or is closer than all the others.
The actual value is 980. His was 961, which is the closest to the actual, which means he's the most accurate. Good? Okay, and then what about Keaton? Can you explain the next part of it for me?
So because of the plus or minus, that's basically them giving the wiggle room, basically saying I could be off this many. And because Paul's number is the smallest, that makes him the most precise.
Good. His measurements are closest together because he's only got plus or minus 4 centimeters per second squared on either side of his measurements. So he's got very little variance or little wiggle room. That's a good way to put it in his measurements. Very nice. Good. All right, our last little section of Chapter 1 has to deal with graphing. This is our last little part of Chapter 1 here. Okay, graphing looks at the independent and dependent variables. How many times have you heard those words, independent and dependent variables? A lot, right? We know which independent and dependent variables are. Okay, so when we're interpreting graphs, we want to take a look at what is the independent and what is the dependent variable. So the difference between the two. Sorry. The reason that we look at graphs in the first place is we want to find a pattern of some kind. Okay, that's the reason that we do any sort of graphing and that we interpret graphs is because we want to find some sort of pattern. Is it a linear pattern? Are they directly related? Are they inversely related? There's all kinds of ways that we can interpret graphs, but graphing gives us the opportunity to find some pattern, okay, to recognize a pattern. Okay, so now we're going to look at the variables and the two different types, independent and dependent variables. Okay. That's fine. Which of our variables is the one that we control? The independent, yeah, or the x-axis. Okay, the independent variable. Okay, the independent variable is the one that we control or the one that we manipulate. Okay, whether that's time or whether that's temperature, Those are usually things that we consider independent variables. Those are what we are manipulating. The dependent variable, however, on the other hand, is what is being dependent upon the independent variable changing. Okay, so that's kind of your results that are coming out. You get to pick the independent variable and you vary it yourself. The dependent variable is what happens there. So independent variable, we said, sits on the x-axis. So the way I remember this is I draw an I, and then I draw a D. Okay? That's how I remember independent and dependent. You might have another way that works best for you. But I'll show that again. The dependent variable sits on the y-axis. The independent variable sits on the x-axis. Okay? So whatever we are controlling should always go on the x-axis. The other thing is going to be varying on the y-axis. Relationships are our most common types of graphs. That's when we have a straight line. Okay? Straight line. Could be up and to the right, could be down and to the right. It could go lots of different ways here. But our linear relationships is when the line of best fit is a straight line. Okay? So the dependent variable lines up linearly, okay, or it directly correlates to the independent variable. Here is our line of best fit equation for a linear graph. Y equals mx plus b. So that would give us the equation for the line of best fit on a linear graph. Okay? This equation right here should look familiar. We use that to find the slope. Right? This is the same as saying rise over run. Okay, because rise is the change in y, or the change in vertical. Run is the change in horizontal, or the change in x. What does this little Greek letter, delta, mean? It means just change in. So delta is equal to change in. Or more specifically, delta equals final minus initial. Okay, we use delta a lot in physics. Okay, so this delta you need to be really familiar with, and I want you to really think of it in terms of final minus initial. So if we want to find the slope, we're going to take the final y-coordinate minus the final y-coordinate over the final x-coordinate minus the initial x-coordinate. Okay, so final minus initial. So you need to be really familiar with what that delta means. Okay, so here's an example of a linear graph. Okay, line of best fit is going to be found by this equation y equals mx plus b. Do we need to talk about this equation, or is everyone feeling good about that? Hopefully everyone's feeling good about that. Okay, this is your slope, your x-intercept, your y, no. Okay, slope, tell me what b stands for? Y-intercept, sorry. This is your x-coordinate and your y-coordinate. Okay, very good. Okay, what if it's a nonlinear? What if the graph is not exactly linear? We're going to just talk about two quick types of graphs here. Okay, a quadratic relationship is when one variable depends on the square of another. So this is when you would look at the quadratic formula. Okay. Okay, so a quadratic formula is when one variable depends on the square of the other. Okay, so we might have our y-intercept is equal to x squared, our x-intercept, or our x-axis. Okay, then our last type of graph is called an inverse graph, when one variable depends on the inverse of another. So our equation there for line of best fit is y equals a over x. So there's our quadratic graph and there's our inverse graph. Okay. So these two are both line of best fit for our quadratic graph. So that means the equation of this line is y equals a squared plus bx plus c. That means this line right here is y equals a over